We've all seen it, right? An AI that can master these impossibly complex games or that powers the next generation of robotics. But have you ever stopped to wonder, how does it actually learn? Well, today, we're diving into the powerful idea behind it all: reinforcement learning. So let me start by asking you a question. How can a machine get really, really good at something, like a video game or even driving a car, without any instructions? Not one. It sounds kind of impossible, doesn't it? Well, this is the exact challenge that reinforcement learning was designed to solve. And the secret to understanding this isn't buried in some super complex code. It's actually much closer to home. It's all about how we learn. Just think about how a person learns something totally new, right from scratch. I mean, picture someone playing a new video game for the first time. At first, they're just mashing buttons, right? We'll call those actions. Then they stumble upon a coin and the score goes up. That's a positive reward. A second later, they hit an enemy and lose a life. That's a negative reward, a penalty. There's no rule book. It's just by trying stuff and seeing what happens, they slowly start to build a real strategy. And that process right there, learning from consequences, that's the absolute essence of reinforcement learning. We just use some slightly more formal words for it. The player, our AI, is called the agent. The game world it's in, that's the environment. And the whole learning process is just the agent interacting with its environment, trying to collect as many of those good rewards as possible. But this isn't just completely random trial and error. There's a real structure to this process, a set of rules that lets the agent learn way more efficiently. So let's take a look at the actual framework. It all works in a continuous loop. First, the agent observes its current state, like where it is in a maze. Second, based on that state, it chooses an action, like I'm going to move right. Third, the environment gives back a reward, maybe a little penalty for hitting a wall or a huge prize for finding the exit. And fourth, the agent is now in a new state. This loop just repeats over and over, maybe millions of times, and the agent gets a little bit smarter with every single cycle. So what's the agent's ultimate goal here? Well, it's not just about getting the next reward it sees. It's about getting the biggest possible score over the long run. This is all guided by this really powerful idea called the reward hypothesis. It's the belief that basically any goal can be described as trying to maximize a total cumulative reward. And this is key, because it means we can apply this kind of learning to almost any problem you can imagine. But this brings up a classic dilemma, one we all face. Is a reward I can get right now worth the same as a reward I might get tomorrow? How should an agent weigh a small, certain payoff now versus a potentially bigger but more uncertain payoff way down the line? This quote just nails it. Imagine you're a mouse. There's a little piece of cheese right in front of you. That's a guaranteed immediate reward. But across the room, there's a huge block of cheese. Awesome, except it's right next to a sleeping cat. The immediate reward is safe. The future, bigger reward is way, way riskier. So what do? This is where something called the discount rate, or gamma, comes in. It's basically a setting we give the agent, a number from 0 to 1 that controls its patience. A low gamma makes the agent really short-sighted. It's going to grab that cheese right in front of it. But a high gamma makes it more patient, more optimistic, more willing to risk it for the big cheese over by the cat. Okay, so the agent has a goal: maximize all the rewards. But what's actually in there making the decisions? We have to actually build the agent's brain, which, in the world of RL, is known as its policy. This policy is the brain. You can think of it as the agent's complete strategy guide. For any possible situation it could ever be in, the policy tells it the best action to take. The whole entire point of reinforcement learning is to find the optimal policy, the one that will get the highest possible score over time. Now, there are two main ways to go about building this brain. First, you have policy-based methods. This is like building a GPS. It directly learns a map of actions, telling the agent, if you're here, do this. Then you have value-based methods. This is more like making a treasure map. It learns how valuable each location is, and the agent's policy is just Always move towards the treasure.
But to learn effectively, no matter how we build the brain, the agent has to constantly solve one of the most fundamental dilemmas in all of artificial intelligence.
It's that classic trade-off, exploration versus exploitation. Just think about choosing where to eat dinner. Exploitation is going to your favorite restaurant. You know it's good, it's a safe, guaranteed reward. Exploration is trying that brand new place down the street. It's a risk, right? It could be awful, but you might just discover your new favorite spot. A good agent has to do both, exploit what it already knows to get points, but also explore to find even better strategies it never knew existed.
So we've pretty much covered the basics of reinforcement learning, but you've probably heard the term deep reinforcement learning thrown around. So what does that deep part actually mean?
It's actually a lot simpler than you might think. Deep just means we're using a really powerful tool to be the agent's brain, a deep neural network. This kind of AI is just fantastic at finding subtle patterns in massive, massive amounts of data, which is exactly what you need when you're dealing with really complex environments. So what does this look like in practice? Well, for a simple game like tic-tac-toe, you could use a classic approach and just store every possible move in a big table. No problem. But for a modern video game, the number of possible states on the screen is bigger than the number of atoms in the universe. A table is completely impossible. And that's where DeepRL shines. We swap out the simple table for a neural network. It doesn't memorize every single state. Instead, it learns the patterns so it can intelligently predict the best action.
So let's just put it all together real quick. Agents learn by trial and error, guided by rewards. Their goal is to maximize the total reward over time. The policy is the agent's brain, its strategy, and it always has to balance exploring new things with exploiting what it knows. And finally, when we use a neural network to act as that brain, it becomes DeepRL. That's it.
You know, this simple framework, an agent learning from rewards, is just incredibly powerful. It's already been used to conquer the world's most difficult games. So the real question is, what's next? If an AI can master a game with these rules, what other massive real-world challenges, from discovering new drugs to managing our cities, can be solved by an AI that simply learns from its results? Thanks for joining this explainer.